Right, so in this video I'm going to have a look at the Leaving Cert Higher Level Maths Paper 2 for 2017, and I'm going to have a look at the last question, which is question 9. So this is a diagram we're given here, and we're told that it's Connor's property which is bounded by a straight bank of a river as shown in figure 1. So here we've got Connor's property, and we've got the two banks here and the river going down the middle. T is the base of a vertical tree that is growing near the opposite bank of the river. So we've got our tree here. TE is the height of the tree as shown in figure 2. So we've got a separate diagram here. So this is our tree here. And we can see C here. And we can see C here from the top view on the opposite bank. So it goes straight across because it's at right angles here. From the point C, which is due west of the tree, the angle of elevation of E, the top of the tree, is 60 degrees. So from C here, the angle of elevation to E here is 60 degrees. So we're given that here. From the point D, which is down here, the angle of elevation, and by the way that's 15 meters due north of C, but the angle of elevation to E is 30 degrees, so this angle here is 30 degrees. The land on both sides of the river is flat and at the same level. Now, first question is, using the triangle ECT, so that's this triangle here, ECT, express TE in the form square root of A times the distance CT meters, where A is an element of n. So we've got to find TE using this triangle here. So I'm just going to redraw that triangle first. So it's going to look something like this. So this is our right angle here, and we have C here. We have T, the base of the tree here, and the top of the tree up here, which is E, and we know this is 60 degrees here. Now we have to use this triangle here to express TE, so this distance here, in the form root A times CT. So we want this side, and we're also talking about this side here. So it looks like here we're talking about the tan of this angle here, the tan of 60 degrees. So let's write that down. Tan is opposite over adjacent. So tan of 60 degrees is the distance TE, which remember is what we need, over the distance CT, which is also what we need in our answer as well. Now we know that the tan of 60 degrees is just root 3. It's one of these special angles. So the tan of 60 degrees is square root of 3. So that's equal to the distance TE over the distance CT. So that would just give me the distance TE, which is what we're looking for, equal to, so multiply both sides by the distance CT. So it's the square root of 3 times the distance CT. That's exactly what we want. So we had to express TE, which we've done, in the form root A, where A is a natural number, so we have root 3, 3 is a natural number, times the distance CT. So we've done that. Okay, so that's the first part of the question. Now show that T may also be expressed like this here. Now if we look at two things here first, we're going to look at two triangles. First triangle we're going to look at here is this one here, CTD. So if we look at this triangle here, we can see that this is 15 meters here, and if you square 15 you'll actually get 225, which is part of what's required in the answer. So we're probably going to have to use this at some stage. We've also got this triangle here, which is which has an angle of 30 degrees in it, and we can do exactly what we did to this triangle here, using the tan to find TE. So we're going to do it this time with this triangle here, with this triangle here, which has 30 degrees in it. But first thing we've got to do is work out what TD is, or DT is, using this shaded in triangle on the ground here, if you like. So let's have a look at that first. So we're going to look at DCT first. Let's just draw that first. So we're going to look at D down to C over to T up again. So this is C here, this is D here. Remember, this was 15 meters, and this is T here. This is our right angle here. What we're going to do is try and find DT, this here. So we can say here that, well, we can use Pythagoras' theorem again. We can say that 15 squared plus CT squared is equal to DT squared. Now if you look here, this is just 225 plus CT squared, and that's equal to our DT squared. And if you look at this here, this is exactly what's in what we're looking for. We've got a 225 plus CT squared here, and we've just worked out that here it happens to be DT squared. Now the next thing we're going to do is, we now know what DT squared is. Well, we can actually work out DT if you like. We'll actually just go one step further. We'll work out DT here, the distance from DT here. It's just going to be the square root of 225 plus CT squared, which is the top line of this fraction here. So now we know what DT is. So if we just go back up to our diagram again here, we now know what DT is. So now I'm going to have a look at this triangle here, DTE, with an angle of 30 degrees. And remember, we have our adjacent here now. Okay, so let's do that. So let me just draw that first. So we have a triangle that looks like this. We have a right angle here. We have 30 degrees here. We have D here. We have T here. And we have E up here. Now we know what DT is. We've worked that out here. So that's along here. I won't write it in, but that's it there. So we're going to use, again, what we did in the previous part of this question. We're going to use a tan of 30 degrees. So we take the tan of 30 degrees. That's going to be equal to TE, the distance TE, divided by the distance for DT, from D to T. We already know that, well, we'll just write down TE up here. We already know DT here is going to be the square root of 225 plus CT squared. The tan of 30 degrees is one of these special angles again, so that's just 1 over root 3. You can look this up in your table, so it's just 1 over root 3. Now if we just multiply across here, I'm just going to cross multiply. We've got a fraction equal to a fraction here, so I can just multiply across by this first and then this here. So what you get is, I'll do it in 2 steps. Well, no, I'll just do it all together. So I'm going to multiply 1 by this here and then root 3 by the TE. So what I end up with is root 3 times TE, the distance TE, is equal to the square root of 225 plus CT squared. So I've just cross multiplied here. Now if I divide by root 3 here, I get a value for TE. So I'll get TE is equal to the square root of 225 plus the distance from C to T squared, all over square root of 3. And you may remember from your rules or your laws of surds, if we have a square root of the top of a fraction and the square root of the bottom of a fraction, you can just combine the two, so you end up with the square root of 225 plus CT squared over 3. And that's exactly what we were looking for. So now we have TE looking like this, and we have TE also equal to root 3 times CT in the first part. So we have 2 different versions of the distance from T to E here. Okay, so let's move on to the next part of the question. This is oh yeah, okay, so we have to find CT now. So it says hence find CT. So we have TE in terms of CT here, and we have TE here in terms of CT as well. So I can just equate these two. So I can make this part here equal to this part here, and then just solve for CT, which is what we were asked to do. So let's write that down. So we've got root 3 times CT is going to be equal to this here, which is the square root of 225 plus CT squared over 3. So now I have an equation here. I have an equation, and in the equation I've only got one unknown. The unknown is the distance from C to T, so I can presumably isolate that at some stage. So the first thing I'm going to do is get rid of this square root here and this one here. I'm going to square both sides. So if I square the left hand side, I'll get 3 times CT squared. Square this and square this. Square the right hand side, you get 225 plus CT squared all over 3. Okay, so let's multiply across by 3. So you get 9 times CT squared is equal to 225 plus CT squared. Okay, so what I'm going to do now is subtract CT squared from both sides, just to bring this, in other words, I want to bring this over here if you like. So I'll have 9 of these CT squareds minus 1 of these CT squareds, so that'll give me 8 of these CT squares. That's equal to 225. The next thing I'm going to do is divide by 8 to get rid of that 8 there, and that will give me, let me see, 28.125. And finally then I'm just going to square root both sides, so that will give me a distance for CT is equal to the square root of 28.125, and we need this correct to 1 decimal place. So correct to 1 decimal place is actually 5.3 meters, and that's to 1 decimal place. Okay, so now we found the distance from C to T. Okay, so that's the distance from the base of the tree directly west over to C. Now, next thing we've got to do is find the height of the tree. Give your answer correct to 1 decimal place. So the height of the tree, we're going to use, let's see, the triangle CTE. So let's just have a look at that. CTE. So we're going to look at this triangle here from C to T to E here. We're going to look at this here. Because remember, we have CT, we have that distance there. We have this angle here. So we can find ET here by looking at the tan of this angle here, 60 degrees. So let's have a look at that. Okay, so find TE. So let's draw the triangle again. So we have this triangle here, we've got 60 degrees here. This is C, this is T, and this is E here. We now know that CT is 5.3, and we've got to work out this distance here. So you can see here that again we can use opposite over adjacent here, which is tan. So we can look at the tan of 60 degrees is equal to the distance ET, or TE, over 5.3. So the distance here from T to E, which is what we were asked to find, is equal to 5.3 times the tan of 60 degrees. So the distance from T to E is equal to, and remember we've got to give our answer correct to 1 decimal place, so we actually get 9.2. So that's the height of the tree here, is 9.2 meters. Okay, next part of this question is where the tree falls across the river and hits the bank at Connor's side at point F. Find the maximum size of the angle FTC. Give your answer in degrees correct to 1 decimal place. So if we look at our diagram back up here, the tree is here, it falls, and just the very top leaf of the tree just hits the bank here. So it just barely reaches the bank. What's the maximum size of the angle FTC. So FTC. So what would this angle in here be? In other words, if I was to draw a triangle across here, what would this angle here be? If the tree was just barely just to hit the bank at the other side. Okay, so let's just draw that triangle and work that out. So let's see, we have F, C and T is what we're going to draw. So we're going to have a triangle that looks like this. Have a right angle here. You've got F here, you've got C here, and you've got T here. Now remember, this is our tree here along here. So the tree has just reached the opposite bank. So the very top of the tree has reached the other bank at F. And we know that the height of the tree is 9.2 meters here. We've got to work out this angle here. And we know as well that CT here is 5.3. We worked that out in part C. So this is 5.3 meters here. So what we're going to do here is work out this angle. Now the two sides we have are the adjacent and the hypotenuse, and the adjacent and the hypotenuse will be cosine. So we're going to look at the cosine, or the cos of this angle theta, is equal to 5.3 over 9.2. That means theta then is just going to be equal to the cos inverse of 5.3 over 9.2. When you work that out, then you get 54.8 degrees. 54.8 degrees, and this is to 1 decimal place as well. Okay, so that's it. So this angle here is 54.8 degrees. Now the last part of this question then is a probability type question. So it says that if the tree was equally likely to fall in any direction, find the probability that it would hit the bank on Connor's side when it falls. Give your answer as a percentage. Well, if it falls to the other side, so let's say this is the bank here, we have the tree base here, and we go up here as well. This here is our tree base at T, this is C here, and this is F. This is where it fell in the previous part of this question. But if it was equally likely to fall, it could have fallen on this side and just hit the bank as well. So this angle here we know was 54.8 degrees. This is 54.8 degrees. This here must also be 54.8 degrees, because it could fall equally likely to fall this direction as this direction in this case, and all these angles in between as well. Now, so in other words, it will hit the bank anywhere between this angle here, or between F here and this point up here. So the total angle here would be twice 54.8 degrees, which is 109.6 degrees. So anywhere within this 109.6 degrees, it will hit the opposite bank. But remember, it can equally likely fall out here, or backwards this way. So there's a total of 360 degrees around which it could fall. So the probability then would be 109.6 over 360 degrees. And that will give you a probability of 0.304444 and so on. That repeats. So as a percentage then, that's 30.4% to 1 decimal place, and that's equal to the probability that it would hit the bank at Connor's side. Okay, so that's it. That's it for question 9, and indeed that's it for the 2017 paper 2.